This video talks about the reactivity of oxygen nucleophiles and nitrogen nucleophiles with carbonyls. We'll start out first with oxygen nucleophiles, and the first subject we'll address is hydrate formation. Carbonyls can be transferred into hydrates in water. The position in equilibrium depends on the R group. For example, if we have two carbonyls that are attached to if we have one carbonyl that has two R groups, then we have 99.9% of the carbonyl favored over the hydrate. Whereas if we change the two carbon atoms into two hydrogen atoms, then we have over 99.9% of the hydrate form. Further, if we change those methyl groups into trifluoromethyl groups, then we have over 99.99% of the hydrate form. The mechanism for acid-catalyzed hydration is a pretty long one, and you'll see that most of the mechanisms in this chapter are quite long. In the first step, what we do is take a lone pair of the carbonyl, and we want to protonate it with hydronium, or whatever acid we have, which could be tosylate or tosic acid or sulfuric acid, more than likely. In a second step, we then have water attack the protonated carbonyl, and we form a compound which has a positive charge on the incoming hydrogen or incoming oxygen. We need to then deprotonate that to make our neutral hydrate. A note about mechanisms. Under acidic conditions, you generally don't want to form a strong base, and there are some exceptions, such as imines and enamines, where we have such a small amount of strong acid that due to the lack of abundance of strong acid, we can form a strong base. Also, under basic conditions, you generally don't want to form strong acids. The next section in this reaction of oxygen nucleophiles with carbonyls focuses on acetal formation. And acetals are groups where you've got two R groups and then two ether functional groups. This happens by treating a carbonyl with an excess of an alcohol, such as methanol is one example, with a hydrogen catalyst. Often the alcohol is used as a solvent in this reaction, and what we produce is water, and most equilibrium favors the carbonyl, and you must remove water to favor the acetal formation. Common acids used in acetal formation are tosic acid and sulfuric acid. These are needed to protonate, again, the carbon. This slide focuses on the mechanism for acetal formation, and as you can see, it's a pretty long mechanism. We need to start out by protonating the carbonyl, and we'll do that with sulfuric acid. And the next step is to attack the protonated carbonyl with methanol, and then we move that carbon-oxygen double bond onto the oxygen, creating a neutral OH group. Now we have a protonated ether, which we need to deprotonate with the conjugate base of sulfuric acid. Note that we commonly don't use the conjugate base of sulfuric acid to deprotonate. Often we use water, but in this case we're using the conjugate base of sulfuric acid because we're removing water, so there's not a lot of water available. We then use sulfuric acid to protonate that carbonyl, and that gives us a good leaving group with water. We then have our carbonyl form. Let's stick with blue there, and eject water, and so this is our dehydration step. And we form a carbonyl-like species with a methyl group attached. So this is similar to the species up here, except now instead of a proton, we have a methyl group. In our next step, then we have methanol attacking the methylated carbonyl to form this intermediate, which is then deprotonated by the conjugate base of sulfuric acid, and now we have our acetal. Again, for this reaction to occur, we need to remove water to favor the acetal at equilibrium. Cyclic acetals can also form, and this is pretty common to use. In this case, we're using ethylene glycol, and in 3 steps, we get the formation of the hemiacetal, and in 4 more mechanistic steps, we get the formation of an acetal. This is just like what we did before, where we've got 2 R groups, and then we have 2 ethers attached to that central carbon atom. It's the same steps as in the hydration reaction. We've got 7 mechanistic steps. So for practice, what is the product of the following reaction? Pause your browser and see if you can predict the product of this reaction. Here we're going to change the carbonyl into 2 ether groups, so we're going to have an acetal product. And then we want to count the number of carbons that we have. We've got 1, 2, 3 carbons that are connected to those 2 oxygens in the glycol group. So that's what we need to put on the product. 1, 2, 3. Acetals can also be used as protecting groups. Follow this sequence of reactions to predict the product of the following reaction. I'll let you put your browser on pause for a moment to see if you can predict the product, as well as the intermediate. So predict the product of each step to get to the final product. The first step of our reaction is to protect the carbonyl. Specifically, we're going to protect the ketone because these reactions don't work on esters. Then we remember from our previous chapter on carbonyl reductions that reaction with lithium aluminum hydride results in the reduction of an ester to an alcohol. Catch my mistake there. I formed a carbonyl where we need to have an acetal there. So now that answer is correct. And then we have an acid catalyzed hydration reaction. So that was a hydration. And that's going to remove our acetal group, because remember that in order for our acetal to be favored at equilibrium, we need to remove water. Now that we have water in place, the carbonyl is reformed and we get a product with a carbonyl and a hydroxyl group. Here's another practice. What is the problem of this reaction? And let me give you a hint. The product is a hemiacetal. And remember what a hemiacetal is something where you have an OH group and an OR group connected to a carbon with 2 R groups. So again, pause your browser and see if you can find the reaction to this intramolecular reaction. So how does this reaction work? Let's go through it in multiple steps so that we can get to the product. We're going to draw a mechanism. In the first step of our mechanism, we'll draw, so we're using sulfuric acid. And we want to protonate that carbonyl. Then the next step of our mechanism, we want to attack the protonated carbonyl with an alcohol. And the alcohol that we're going to use is this internal alcohol and the reason that we're going to use that is that intramolecular reactions are faster than intermolecular reactions. Now we want to put our product together. And here we've got an OH group. And let's make sure that we've got the right number of carbons in our ring. So I'm going to use the green marker to count 1, 2, 3, 4, 5, 6 atoms in our ring. So when we put that oxygen together, we want to form a hexagon. What's missing here? We still have a proton on the oxygen that underwent nucleophilic attack. So in our next step, we need to take the conjugate base of sulfuric acid to remove that proton. And then we form our final product, our hemiacetal, which is this compound. Our next section focuses on nitrogen nucleophiles. We're first going to start with reactions of primary amines, and then we're going to go to reactions of secondary amines. Reactions of primary amines form imines via a carbonyl amine. So here's an example reaction that shows how that works. We've got a ketone in this case reacting with a primary amine. Let's put that 2 there. And we have an acid catalyst. And note that this reaction is showing the loss of water, which means we're undergoing a dehydration reaction. So our first intermediate here is the formation of a carbonyl amine, and the second is our product, an enamine. On the next slide, we'll look at the mechanism for how this reaction works. In enamine formation, unlike acetal formation, we're going to conduct this reaction without the protonation of the carbonyl. And how does that happen? Here we have a concentration of H+ that's so low that it's not enough to protonate the carbonyl. So instead, our primary amine attacks the carbonyl, forming this Zwitter ionic intermediate. In the next step, we protonate our alcohol, and we're going to protonate it with specifically the protonated form of our amine. And why are we going to do that? That's because our amine is in excess, so any acid that's present is going to protonate our primary amine to make this tetra-substituted nitrogen atom. And that serves as the source for our acid. Then, in the second step, we need to remove a proton from the nitrogen to make this compound neutral. You can see that these reactions in general are basically proton transfer reactions, and that's what we're going to do in the next step, is again another proton transfer to protonate the water. Let's give that oxygen the positive charge that it deserves. And in our next step, we're going to undergo a dehydration reaction. And we form this intermediate. that is basically the product, the protonated version of our product. So all we need to do to get to our product is to use an equivalent of our neutral amine to remove a proton and give a lone pair to the nitrogen atom. Let's do another practice example. Draw the product of the following reaction. So I'm going to give you a moment to put your browser on pause to see if you can identify or predict the product of this reaction. In this case, our product, again, we want to change that carbonyl oxygen into a nitrogen. So we're going from oxygen to nitrogen using the nitrogen of our in this case, ethylamine. And then we want to attach ethylamine, and let's complete that cyclohexane ring. Carbonyls can also react to form oximes and hydrozones, and that happens by the reaction of hydroxylamine to form oximes and hydrazine to form hydrozones. In this reaction, again, we're starting with carbonyl carbons, and we're reacting with a source of nitrogen, and we are incorporating the nitrogen here, and then we have either oxygen there or nitrogen there. These mechanisms are similar to imine formation, so I'm not going to go through them. Now we're going to talk about the reaction of carbonyls with secondary amines, and these form a product that's called an enamine, and they also go through an intermediate, the carbonyl amine. So here we're starting with a acetone as our example, and we're using dimethylamine as our nucleophile. And then the two methyl groups that are here are now the two methyl groups in our product. And what stands out that's unique about this product is that we have an alkene. And why is that? That's because we can't form a double bond to the nitrogen in this product. So instead we're going to form a pi bond with two carbon atoms. Let's go through the mechanism of enamine formation. Just like the formation of imines, the first step is going to be attack of a carbonyl carbon with our neutral amine compound, and we're forming the Swidder ionic intermediate again. That gets protonated by our protonated amine, and remember that that is the source of our acid, because what little acid is present here is being used to protonate the amine, which is present in excess. Then we need to deprotonate the nitrogen atom to get to our neutral amine, our carbonyl amine. And then what we need to do is make water a good leaving group. How do we make water a good leaving group? We protonate it with the protonated nitrogen atom of dimethylamine, and we get to a protonated oxygen, which is now a good leaving group. So we make that leaving group depart, bring our lone pair on nitrogen down to form a pi bond, and now we have our precursor to the enamine. And how do we get there? we have a proton on the carbon adjacent to the imine, and we're going to use neutral diethylamine to form a pi bond, and we want to give that carbon-nitrogen pi bond to nitrogen as a lone pair. Let's do a little practice. I want you to predict the starting materials of this reaction. So we're going to be adding water to get to the products. So pause your video and see if you can predict the products. Here we want to be replacing our carbon-nitrogen bond with a carbon-oxygen bond, and we also want to be removing this pi bond around our cyclohexene ring in this case. So our starting materials are going to be cyclopentanone as well as diethylamine. The next reaction and last reaction of this video that we're going to discuss is the Wolff-Kishner reduction. Here we're starting with a hydrazone compound. Let's label that. And we just saw that you can get to a hydrazone from a carbonyl reacting with hydrazine. In the Wolff-Kishner reaction, we are using potassium hydroxide and water to transform this hydrazone into a compound that contains 2 hydrogens in its place. So that's a pretty nifty trick in order to get to a functionalized intermediate into one that has no functionalization. So this is another way to turn a carbonyl into a compound with only 2 hydrogen atoms in its place. And this is similar to the chemistry that we have in the Clemmensen reduction, where we transform a carbonyl into an alkane attached to a benzene. What I should point out is that this reaction is not limited to benzene rings, that the benzene ring could be an alkyl ring as well, an alkyl group as well. However, let's check out the mechanism for this reaction. Here we've got a strong base, so what are we looking for? We're looking for deprotonation. Our strongest acid is on the amine, so we're going to take a proton from that, and let's make that a lone pair. These are just resonance structures of each other, and then we're going to bring our pi bond here down to form a lone pair on the carbon atom. So trying to label that in green there, but let me go back and do that with green highlight instead. There we've got a pi bond, now it's a lone pair. In the next step of our mechanism, we need to protonate that position, and we're going to use water here, and we're generating a strong base hydroxide again. That can be used to deprotonate this molecule again. Here we form nitrogen gas, and we're left with another carbanion. This is attacked with water to form, again, our alkane, in this case a benzylic alkane. But recall, as I said in the last slide, this does not have to be a benzylic position. So that's all for this video. I hope that you can follow it, and certainly watch it again if you need to follow these long mechanisms again. But just remember that these are mostly proton transfer reactions.